Let's go over some related rates involving triangles from what we did. So if we look at 9b, it says a man 6 feet tall walks at a rate of 5 feet per second toward a street light. So here's my little guy walking towards this street light, which is 16 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base? Alright, so let's label everything. So we can call this piece X, this piece Y. If he's walking towards the light, his shadow is over here. The man is 6 feet tall, and we want to know, let's see, he's walking at a rate of 5 feet per second towards a street light. At what rate is the length of his shadow? If this is his shadow, we want to know dy over dt. Right? What is the rate of the length of his shadow changing when he is 10 feet from the base of the light? So here he is. We want x. So this is when x equals 10. Now it says that he walks at a rate of 5 feet per second. So here's where sometimes it can be tricky, but he's walking. We already have dy over dt. That's his shadow. So then we can use this other piece where he's walking. So dx over dt is the rate at which he's walking, which is 5 feet per second. And so we are looking for dy over dt. So when we look at this triangle, we need to see how can we relate x and y to get an equation where we can take the derivative. So x is here, y is here, so I cannot use Pythagorean theorem, but if you notice we have this one big triangle and this one little triangle, and so we can use proportions from similar triangles. So we can see that this big side, this length of the big triangle is to this side, so if we have 16 is this whole bottom side, and that's the same as this little triangle. 6 is to y. Now 16 is the height of this lamppost, so this is a constant. I can put this in this equation. 6 is also the height of the man. That's also a constant. So before I take the derivative, I can only use constants in my equation. Well, since this equation has both x and y, which are my two, the two related rates, I can go ahead and take the derivative now. So first I'll cross multiply, so I get 16y equals 6x plus 6y. I'll subtract 6y over here to get 10y equals 6x. Now I can differentiate implicitly with respect to time. So I have 10, and this is derivative of y with respect to t. 6, derivative of x with respect to t. Now let's see, we're looking for dy over dt. I know that dx over dt is 5, so I can dy over dt equals 6. This is 5. And I can divide over the 10. And so 6 times 5, 30 over 10, I get 3 feet per second. All right, so now how does that compare to number 2? Number 2. So here we have a light is on the ground 20 meters from the building. So my light's on the ground. There's the building. It's 20 meters from the building. And it says a man is 2 meters tall, walks from the light directly towards the building at 1 meters per second. So let's just again label some things here. Okay. How fast is the length of his shadow? Well, if the light's behind him shining this way, we know his shadow is on the building. The shadow's over here somewhere. And we want to know how fast the length of his shadow. So since I represented where his shadow is with an h, this is what we're looking for, dh. This is what we're looking for when he is 14 meters from the building. Well, here's his distance from the building. He's walking towards the building. So this is when x equals 14. So now I need to decide, he's walking, and is it dx over dt? Is it dy over dt? Does it matter? Well, it only matters, we need to use the side which we're going to be able to work with our similar triangles. So I know I'm comparing this height, right, because I'm looking for dh over tt, so I need this big triangle, so this piece here, I need to compare it with this little triangle, So I'm going to use y, dy over dt, as his walking rate. Really, it doesn't matter. This whole piece here, he's walking towards the shadow, towards the building. And so you have to choose the one which is going to work out with the whole problem. So dy over dt, that's him walking 1 meter per second towards the building. All right, so again, we need to use these proportions in the similar triangles in order to solve this. We need dh, we need dy. So how can we compare? Again, this h, well, can only be compared to this x plus y. And, well, 2, that's my constant, that's how tall he is. Well, I'm comparing that to y. And so I want dh, and I want dy. I don't want x plus y, so, but guess what? 20. Oh, that's my constant. That's a constant because this is the distance that the light is from the building. So I can use 20 in here. Remember, only constants. And I can do that because this is a constant. The only thing changing here is the distance between x and y. This is what's changing. Alright, so now we can go ahead and h times y equals 40. And so I can now differentiate this. But look here, I have a product. I have h times y equals 40. So I have a sidebar, do my product rule. And so this is dh over dt, this is dy over dt. And so my derivative here is h times dy over dt equals, plus y times dh over dt, and this all equals derivative of 40 is 0. And so we're trying to isolate dh over dt, so I have y dh over dt equals negative h dy over dt. I just subtracted that over. I'm going to divide by y. So I have dh over dt equals, well, I have to figure out what h is. Dy over dt, I know that's 1, so I don't have to write 1. And y, well, again, if we're looking at this moment, we found the derivative at the moment when x equals 14. So if x is 14, then that means y equals 6. But I now need to find h. And so let's go back to our triangle. I have h. Again, I can use my proportions. I know this whole side is to this whole big side. So h is to 20 as this little triangle 2 is to 6. I can use this here because, again, I'm finding the derivative at the moment when, if this guy is 14, then this guy is 6. So this is the moment that counts. So now I can solve this out. 6h equals 40. Therefore, h equals 40 over 6, which is 20 over 3. And so I have dh over dt equals negative 20 over 6 times 3 is 18. which can reduce to negative 10 over 9 meters per second. So I got my final answer. Well, why is it negative? Well, remember what we're talking about. The man is walking towards the building. So even though his shadow might be getting bigger as he walks towards it, the rate at which it's getting bigger is slowing down. Remember, this is a rate. This is a rate. So the rate is slowing down. The shadow may still be getting bigger, but the rate at which it's getting bigger is slowing down. Okay, so now let's look at one involving the Pythagorean theorem. So from the other day, we have an airplane is flying towards a radar station at a constant height of 6 kilometers above the ground. So my airplane here is up in the sky. Here's my airplane. I'm not even going to try to draw that. And the radar station, I don't know, somewhere over here. And so from the ground, here's my distance, airplane from the ground. I'll just connect now these dots. And so I have a triangle. So here's my airplane flying up here. Here's my radar station. Radar station. And so let's see. A constant height of 6. So this is my height up here. This is the constant. Constant height of 6 kilometers above the ground. If the distance s between the airplane and the radar station is decreasing at a rate of 400 kilometers per hour when s is 10 kilometers, what is the horizontal speed of the plane? So ds over dt is decreasing, so it's negative 400 kilometers per hour when s equals 10. What is the horizontal speed? So this horizontal up here is the same as this horizontal down here, right? Because if we actually drew this all out, this would be a parallelogram, and opposite sides would be parallel and congruent. So that's why I can use this line here, which, I don't know, we'll call x, and so we're looking for dx over dt when s equals 10. Okay, so again, so this is a right triangle because this is my vertical distance, plane to the ground, and I need to relate these three sides. I need to make a relationship between s and x. So I know that this side, which is 6 squared plus x squared equals s squared. So again, 6, that was my constant. That's my the airplane is constantly 6 kilometers above the ground. And so these are my variables, which is what I need. So this would be the equation that I take the derivative of. And so derivative of 6 squared is 0 plus we have 2x dx over dt equals 2s ds over dt. And so I'm looking for dx over dt, so I'll isolate it. So I have dx over dt equals 2s ds over dt divided by 2x. So those cancel. And so I have s over x ds over dt. So now I need to plug in what I know. I know ds over dt is negative 400. I know s equals 10, but I don't know x, but I can find x. So just like we did in the previous problem where we found one of the variables after we found the derivative, because this distance can change. Okay, so when s is 10, I have 10 squared equals 6 squared plus x squared. And so solving this out, I get x equals, let's see, what do I get x to equal? 8. All right, 100 squared minus 100 minus 36, I get 64, yeah, so this is 8. And so now I can plug in 10 divided by 8 times negative 400. So let me plug that into the calculator. And I get negative 500 kilometers per hour. Would this be negative though? Let's see. Nope, this would be positive because they're already telling me this is decreasing. So yeah, this guy would be positive. It would be positive. We're talking about the speed of the plane. So it's 500 kilometers per hour. I hope this video helped. And just to reaffirm, we knew this had to be positive, but when I subtracted this over, that made this negative. So we have a negative and a negative, but we knew this had to be positive anyway. Okay, hope this was helpful.